Okay, in this video we're going to talk about reduction and oxidation reactions. Reduction, the term, was originally used to describe when we took a metal compound, something like copper sulfide as our example here, and we reduce that metal back to its pure metallic form. What we're going to see as we go through this process is that reductions result in a reduced oxidation state. Now I know we don't know what oxidation state is yet, so I'm going to go through that, and then I'm going to go through it briefly in this video, and then I'll go through it in much more detail in a subsequent video. And to reduce your oxidation state, what that means then is that you will be receiving or you will be gaining electrons. Let's look at copper sulfide in this process. Copper would be 2 plus, and the sulfur would be 2 minus, and this would be an ionic compound. During the reaction, focusing on copper, he's going to go from, this is the oxidation state, the 2 plus, from that oxidation state to becoming pure copper. If he was copper 2 plus, to go back to being copper regular, he must have gained 2 electrons. If we were looking at copper's valence electron shell, it would have been empty, and then as 2 plus, and then to convert to copper regular, it would have gained 2 electrons back with its effective nuclear charge of +2. An oxidation state refers to the charge of an atom in a compound. It does not need to be an ionic bond for us to use the term oxidation state. So typically we only say ionic bonds form actual ions. But for the sake of oxidation states, any atom in any bond, we're going to assign an oxidation state. The way we're going to do that is if we have shared electrons, whoever has the higher electronegativity will be assigned the electrons in that bond. So let's take, the simplest example, water. And when trying to find his charge, I'm going to look at the effective nuclear charge, or the number of unscreened electrons, and recognize that it has +6, right? Let's just quickly go through that. It has 8 protons, 8 neutrons if I'm doing the Bohr-Rutherford for oxygen, and 2 electrons in the first shell, and 6 electrons in another shell. And these 2 electrons and these protons shield each other or interact with each other to create an effective nucleus for chemical reaction purposes of +6 and 6 valence electrons before bonding. Now then you can bond and all that kind of stuff. If you're not familiar with the idea of effective nuclear charge, I'm going to recommend that you go back at this point and look at videos that I made a lot earlier searching effective nuclear charge to make sure you understand that. Anyways, so the oxygen has +6 from the unshielded protons in the nucleus, and it has 2 electrons here and 2 electrons here. He's not sharing any of those, so he gets all of those for sure. But the electronegativity of oxygen is 3.5, and hydrogen is 2.1. So even though this does not classify as an ionic bond, for the sake of the oxidation number, we're going to give oxygen both of these electrons, and so it's going to get 2, 4, 6, 8, minus 8 electrons, and its oxidation state is going to be -2. So that's what an oxidation state is. Again, I'm going to do a whole nother video where I talk about these in detail, but a reduction reaction can be thought of as either reducing a metal to its pure metal state from a oxidized or a compound metal, or it can be thought of something that reduces the oxidation state. So here in this atom, or in this ion, its charge would be 2 plus, so that's its oxidation state. And after the reaction, he's sitting over here as an element, and so his oxidation state would be 0. So it went from 2 plus to 0. That is a reduction. How did it get reduced? It gets reduced by gaining electrons that can cancel that positive charge, And so a reduction is gaining electrons or reducing the oxidation state. Oxidations are the opposite to that. Oxidations are typically viewed as were historically viewed as when atoms or elements reacted with oxygen, or compounds reacted with oxygen. This results in them going to a higher oxidation state, and the reason that they go to a higher oxidation state is they typically lose their electrons to that oxygen. This term has been generalized since then to refer to any reaction where the oxidation state of the substance is increased. It does not have to be a reaction with oxygen. But for a little example here, I've just done a simple reaction with oxygen. So carbon, in its elemental form, would have had its +4 effective nuclear charge and still being responsible for 4 of its own electrons. And so as an element, it would have had an oxidation state of 0. And then when it reacts with the oxygen to form carbon dioxide, the oxidation state of these O atoms would be +6, but they get credit for all of these electrons because the electronegativity of oxygen is, I want to say 3.5, I just looked at it. Yep, 3.5. And the oxidation state of carbon is 2.5. Or the oxidation state, sorry, the electronegativity. So since this one is greater, it gets credit for all of those electrons. 2, 4, 6, 8. So it has an oxidation state of -2. Carbon, on the other hand, now has credit for none of his electrons because he's bonded with 2 oxygens. Those oxygens haven't stolen those electrons, like we would say in an ionic bond, but from the point of view of an oxidation state, they're dominating, they're taking them for the most part. So now copper has an effective nuclear charge of +4, and then there's 0 electrons associated with it, so it has gone to an oxidation state of +4. So 0 to +4. And how do you get something to go from 0 to +4? Well, you get it to give away 4 of its electrons. Who does it give its electrons to? Well, most typically, the most common atom that's going to be stealing those electrons is oxygen. So we call this an oxidation reaction, where the atom loses electrons and goes to a higher oxidation state. Now, I think what we need to do before we go any further in this is we need to spend some more time really understanding what oxidation states are. So I'm going to stop here on this video, and I'm going to go into another video where I really look at oxidation states more clearly.